Let's calculate the moment of inertia for a wide flange beam. In this case, I've chosen a beam that's known as a W12 by 87. The W just stands for wide flange. 12 means this dimension here is nominally about 12 inches tall. And the third variable is 87, and that stands for pounds per foot. So this would give you the weight of the beam. So each foot of the beam weighs 87 pounds. And there's all sorts of these W12 beams. They range anywhere from W12 by 14 up to W12 by 136. So it means that each beam, the different sizes, could range anywhere from 14 pounds per foot up to 136 pounds per foot. And all of them nominally have this dimension of about 12 inches. And although this dimension stays at about 12 inches, what changes to change the weight is mainly the width of the flange. So a lighter beam would tend to have a narrower flange, and a heavier beam tends to have a wider, thicker flange. Let's start by defining the coordinate axes. I'll run the x-axis down the length of the beam, the y-axis vertically, and the z-axis sticking out in the other direction. When we look at the section on the right, this dot in the middle represents the centroid. And from this direction, y-axis upward, z-axis to the left, and the x-axis comes straight out at us. Typically for a wide flange beam, a load would be applied downward to the upper flange, and the beam would tend to bend about the z-axis. And consequently, we want to calculate the area moment of inertia about the z-axis, and that's equal to the integral of y squared dA, where y is the vertical distance from the centroid. Note that how you typically see this reported in reference manuals, you'll typically see this being the x-axis and this being the vertical axis. I'm keeping it the z-axis to be consistent with the isometric view. But just keep that in mind. What we're calculating, what I'm calling IZ, you'll typically look up, and it's called IX. To evaluate this integral, let's break the cross-section into three parts. The first will be the web, the vertical component. It's a rectangle. I'll use lines here to delineate the rectangle. The second part is the upper flange, part 2, and the third part is the lower flange, part 3. There's a few other dimensions that we need to make the integration a little bit easier. The first one here is this dimension is 6.0625. Simply 12.125 inches divided by 2. And the other dimension that we want is this dimension, the distance from the centroid to the bottom of the upper flange, and this is 5.455 inches. And the other dimension that we'll want is the distance from the centroid to the top of the upper flange, and that's 6.265 inches. Here's the integral from the web, and I'm integrating with respect to z, the left side of the web, to the right side of the web. And for y, I'm integrating from negative 5.455, so down here, up to a positive value of 5.455 at the top of the web. And that'll evaluate that y squared dy dz. I can do something similar for the upper flange. I'm integrating again from the left, negative 6.0625, to the right of the upper flange. And I'm integrating from the bottom of the upper flange to the top of the upper flange. And I'll do something real similar for the lower flange. These integrals are straightforward to evaluate. Here's the for the web for the upper flange, and zone 3, the lower flange. When I do the arithmetic, I'll come up with IZ equal to 731.3 inches to the fourth. When you look this beam up in a handbook, you'll find a value IZ reported to be 740 inches to the fourth. And I think that the difference that we're seeing here between this very small difference between the two is the fact that in a real beam, there'll be welds at the top and bottom of that. And I think that that difference accounts for the welds. What's interesting is just how little of a difference the web actually makes in terms of the area moment of inertia. For example, if we forget about the web altogether, delete that first term, I compute an area moment of inertia of only about 676 inches to the fourth power. What this means is that the presence of the web, although its area is nearly a third of the entire cross-section of the beam, it only increases the area moment of inertia by about 8%. It really doesn't make much difference at all in terms of stiffness about the z-axis. The high moment of inertia about the z-axis is due primarily to the flanges, and it's due primarily to the flanges because they're spaced so far away from the centroid. For example, here's a simulation that I ran for a beam that supports a downward load across its flange, and the two sides are both pinned. So it's a simply supported beam with a downward force. And what we observe is the top of the beam is under compression. The material at the top of the beam is trying to be squeezed together, and the material at the bottom of the beam is being pulled apart as that beam is being separated. So the bottom of it is under tension. When we look at the cross-section, I've cut a cross-section down the center of the beam where the bending moment is the greatest. And what we observe is that, again, the majority of the normal stress is supported by the top and the bottom flange. Areas of white means that there's no normal stress at all. We'll see an area of white down the neutral axis of the beam. So if you want to make something as stiff as possible about a particular axis, it's good to move as much material as you can away from the central axis. And this is why wide flange beams are designed the way they are. They're designed to support loads acting on the top flange. Another possibility is to load the beam from the side. So here I've applied a force along the right side of the beam, and if we look at the cross-section, we'll see that the right side of the cross-section is under compression and the left side of the cross-section is under tension. In this configuration, the web itself supports very little, if any, bending or normal stress, and the upper and the lower flanges, there's a significant fraction of the flange that doesn't support any normal stress either. In this configuration, you'd be looking up IY, and when I look it up, I get a value of 241 inches to the fourth power. In this configuration, the flange is only about 1/3 as stiff.